Greetings of the day to all of you. Well, today I'm going to deliver yet another lecture on electric drives. Today is Thursday, 12th January 2023, and it will be lecture number 7. I'll be delivering lecture number 7. Well, uh, in our previous 6 lectures, we have discussed about introduction to electric drives. In the very first lecture, I discussed about what a drive means, what are the types of drives like mechanical drives and electrical drives, advantages of electrical drives over mechanical drives, various components of electrical drives, and the functioning of various parts, various components of an electric drive. Then we have also studied about dynamics of electric drives. We have developed the mechanical equation of an electric drive. And then we have studied about various types of loads, various different types of loads with different torque speed characteristics. And we have also studied about how to find the steady state operation. How to find the operating point uh, of a drive. The operating point of a drive can be very easily found by the intersection of torque speed characteristics of the motor and the mechanical load that it drives. And we have also studied about steady state stability of an electric drive. Once you find the operating point, whether this operating point is a stable equilibrium operating point or an unstable point, we have developed some mathematical relation and some analysis has been done to find whether the operating point is stable equilibrium operating point or not. We have also studied about the load equalization in the previous lecture, lecture number 6. Now, having completed the fundamentals of electric drives, the basics of electric drives, now we will go to the main discussions. First of all, in the first part of the discussions in a series of lectures, I'll be discussing about DC motor drives, and that will be followed by AC motor drives. So from today onwards, in a series of lectures, I will be starting my discussions on DC motor drives or DC drives. DC drives. A DC drive uses DC motor, any type of DC motor as a prime mover. Okay? Whereas an AC drive uses AC motor as a prime mover. So since we are discussing the DC drives use DC motors as their prime movers. To begin with, we will go for a review of torque speed characteristics. Briefly, we will review the torque speed characteristics and methods of speed control. Methods of speed control of DC motors. We'll take different types of DC motors and we will try to study about their torque speed characteristics and methods of speed control. I'm sure all of you must have studied about torque speed characteristics of different types of DC motors like DC shunt motor, separately excited DC motor, DC series motor, compound motors, and you must have also studied about the speed methods of speed control of DC motors, various types of DC motors. In today's lecture, I'm going to just brush up what you have already studied about the torque speed characteristics and speed control techniques of DC motors in your electrical machines course at BTech level. So first of all, we will take DC shunt motor. And of course, we'll take separately excited DC motor because the characteristics of separately excited DC motors and DC shunt motors are somewhat similar. Separately excited DC motor. So let us discuss about torque speed characteristics and methods of speed control of DC shunt motor and separately excited DC motor. A DC shunt motor looks like this. Let me draw the equivalent circuit diagram of a DC shunt motor. This is the equivalent circuit diagram of a DC shunt motor. This is the applied voltage. Let's call this voltage as V. This is armature circuit resistance Ra. There is the resistance of armature winding and plus resistance of the brushes. The current flowing is Ia. The total current flowing is I, out of which current flowing in the armature circuit is Ia. The back EMF developed by the motor is Eb, and this is the field winding. Since this is the shunt motor, the field winding is connected in shunt or across the armature. This is field winding resistance plus maybe some external resistance RF, and this is the field current IF. So this is the equivalent circuit diagram of a DC shunt motor. What about a separately excited DC motor? Let me draw the equivalent circuit diagram of a separately excited DC motor very quickly. This is a separately excited DC motor. This is the back EMF. This is armature resistance Ra. The motor armature is directly connected across the DC source V. It draws a current or armature current Ia, and the field winding is not connected across the motor. The field winding is separately excited. This is the field winding. Let me show you the field winding. And of course, you may have a variable resistance in series with field winding. This is the field voltage Vf, and field current is If. In case of shunt motor, the field winding and armature winding are excited or connected across the same source, so that whenever you change, the source voltage, it changes both armature current as well as field current. They are coupled. Whereas in separately excited DC motor, the armature current and field current, they are decoupled. They can be independently controlled. The armature voltage or DC source voltage controls the armature current, and the field voltage controls the field current. So this is the equivalent circuit diagram of a separately excited DC motor. Let us try to derive the torque speed characteristics of shunt as well as separately excited DC motor. We know if you apply the Kirchhoff's voltage law KVL in this circuit, so I will write by KVL, the applied voltage V is equal to EB, that's the back EMF, plus the voltage drop across armature resistance, that is plus IARA. Let's call this equation as equation number 1. Okay. We also know that in a DC motor, the back EMF is given by K phi omega m. It is directly proportional to flux, and it is also directly proportional to speed at which the motor runs. I'm not going into the details. I'm not going into the derivations. You have already done this in your electric machines course at BTech level. These equations, I'm sure you must have already derived. So this is the back EMF of a DC motor, which is given by K phi omega m, right? We also know that the torque developed by a DC motor, whether it is shunt motor or separately excited DC motor or series motor or compound motor, any type of DC motor, the torque developed by the motor is given by this equation K phi into Ia. Okay, so from this you can find armature current. Armature current is given by T by K phi. Let us call this equation as equation number 3, right? So we can now write from equation 1, V is equal to EB plus IARA, or we can write EB is equal to V minus IARA. Let us call this equation as equation 4. Now substitute the value of EB here and also substitute the value of Ia from equation 3 into equation 4. That means I will write here substituting equations 2 and 3 in equation 4 gives, what does it give? It gives EB. EB from equation 2 is K phi omega m. So instead of writing EB, I will write K phi omega m is equal to V minus Ia into Ra. What is Ia? Ia is T by K phi, okay, into Ra, right? This is from equation 3. IA value, armature current is T by K phi, and I have substituted that here. So from this you can find the expression for speed. So the expression for speed is like this. So therefore, speed of the motor omega m is equal to V divided by K phi, because this K phi will divide here when it goes to right hand side, minus uh, T by, you already have K phi. K phi into K phi is K phi whole square into Ra, armature resistance. That is here. Or we can write that the speed of separately excited DC motor is V upon K phi minus Ra by K phi whole square into torque. So this is a very, very important equation. So this equation can also be written as omega m is equal to omega m naught minus K into T, where what is omega m naught? Omega m naught is equal to V by K phi. It is no load speed of the motor. It is the speed of motor when it is at no load. And what is K? K is equal to Ra by K phi. Let's call this K dash. K dash is equal to Ra by K phi whole square is slope of curve. Whatever curve torque speed characteristic you will get from here, slope is given by Ra by K phi whole square. Okay. So this is the no load speed, and this is the, in fact, you can say this is the slope of the curve multiplied by torque. It gives the drop in speed. When the motor is on no load, torque is equal to 0. So omega m is V by K phi, that is equal to omega m naught, no load speed. But as you start loading the motor, this term increases. So this drop in speed also goes on increasing, so that there is a drop in speed when you go from no load to full load. So therefore the characteristic will look like this. The torque speed characteristic from this equation, if you plot this equation, the torque speed characteristic will look like this. This is the speed of motor, this is the torque developed by motor, and this is the speed of motor. This is no load speed, omega m naught, okay, which is equal to V by K phi. Then as you go from no load to full load like this, there is slightly drop in speed. For example, this is the full load. This is full load torque here, TFL, full load torque. At full load torque, the speed is not same as no load speed. The speed is this much. This is the speed at full load. Let us call this speed as omega m. And what is this omega m? It is no load speed V by K phi minus drop in speed. And what is the drop in speed? Ra by K phi square into T. In fact, this Ra by K phi is the slope of this torque speed characteristic. So this is how we obtain the torque speed characteristic of a separately excited DC motor. And in fact, this characteristic is valid for DC shunt motor also. Okay. So this is about torque speed characteristic of a DC separately excited motor. Now, how to control the speed of DC motor. Now, speed control techniques we'll study. Speed control techniques of DC shunt motor and separately excited DC motor. There are different methods of speed control. First is armature resistance. You must have, I'm sure you have already studied speed control techniques of DC motors. First method is armature resistance control method. Armature resistance, or it is also called rheostatic control. This is first method and easiest method of speed control of DC motor. Second is armature voltage control method. You can also call this voltage control method or armature voltage control method. And third is field current control or flux method. Flux control method, field or flux control. So these are three methods by which you can control the speed of a DC motor. Let us take separately excited DC motor and see how we can control by speed by these three methods. As far as first and second method, is concerned, using first method, that's armature resistance control method, and the second method, armature voltage control method, you can achieve speeds below the rated speed or below base speeds. So you will achieve speeds below base speed. What is base speed? Base speed is the speed at which the motor runs corresponding to its rated voltage and rated flux. When there is rated flux in the machine and you are applying rated voltage across the armature terminals, the motor runs at a speed which is called base speed. So if you want to get speeds below the base speed, then these two methods are valid. That's armature resistance control method and armature voltage control method. However, in some applications, you may require speed above base speed. If you require speeds above base speed, then in that case, this field or flux control method is used. So this flux control method gives speeds above base speed. Okay, so let us take these methods briefly one by one and study them and see how speed control is achieved. So the first method is armature resistance control method. Armature resistance control. Armature resistance control method. So in armature resistance control method, as the name signifies, what we do, we put a resistance in series with armature circuit. It is something like this. See what we do. And it is the easiest method of speed control. We put a resistance R, in external resistance, in series with the armature. Now this R is armature resistance, that's the resistance of armature winding plus external resistance. So let us consider it, say for the time being, we consider it external resistance. Of course, when you take the calculations, make the mathematical calculations, then this R will not be external resistance only. It will be external resistance plus resistance of armature winding. So it will be R dash plus RA. So this is the variable resistance, external resistance that we are putting in series with the armature circuit. What is the applied voltage? Applied voltage across armature terminals is V. And this is its field circuit. In the field circuit, what we do is that we keep the field current constant. So applied field voltage is applied, rated field voltage is applied, and field current is constant. So IF and V are rated field current and rated applied voltage. So these are kept constant. We don't change them. So field current is maintained constant. Applied voltage is also constant, but this armature current we don't maintain constant. We change the armature current with the help of this external resistance. By inserting the resistance in the path of current, IA is changed. And not only IA, the actual voltage which is applied across the armature terminals, that is equal to the source voltage minus this drop. So this voltage is varied. This voltage is varied by varying the resistance. We already know from the torque speed characteristic or from the speed equation, just few moments back we have derived this equation. Omega m is V by K phi minus RA, or you can say R divided by K phi whole square into T. We already know. So in this case, applied voltage is constant. We don't change it. Flux is also constant because field current is constant. We don't change. What we change is R. So when we change the R, resistance, external resistance in series with the armature circuit, or in other words, when we change the armature resistance, what happens? The slope of the curve changes. And since omega m depends upon the R, or it depends upon the slope, when you change R, the speed also gets changed. So therefore, speed control is very easily done simply by changing the armature resistance. When you change the armature resistance, as per this equation, when R is changed, speed also changes. So let us draw the torque speed characteristics and see how speed control is achieved. So this is torque along x-axis and speed omega m along y-axis. This is the no load speed omega m naught, which is equal to V by K phi. We already know. And this is torque speed characteristic for, say, R equal to R1. Say R is equal to R1, there is no external resistance, and let us say this R1 is the resistance of the armature circuit itself, no external resistance. Okay, and then what we do is that we increase the external resistance in series with the, we put external resistance in series with the armature and increase it gradually. So this is R equal to R2, where R2 is greater than R1. So we have increased the resistance, armature resistance. So what happens as per this equation, when R is increased, the slope increases or the drop in the speed increases. And what happens to speed? Speed decreases. So slope is increasing, you see. Then you can increase the slope again. This is R equal to R3, and we can do it again, R equal to R4. Okay, and let us suppose this is the rated torque, load torque. This is load torque, TL, rated load torque, or may not be rated. So let us suppose this is the torque required by the load. It may be rated torque or it may be below rated torque. Okay, now fine. When R is equal to R1, what is the speed at which the motor is running? This is the speed of the motor. Let us call this speed as omega m1. At R equal to R2, the slope of torque speed characteristic increases and the load torque characteristic intersects the motor torque speed characteristic here, and this is the operating point. This is the operating point, and speed is omega m2. At R equal to R3, the operating point is here, and this is the speed omega m3. And at R equal to R4, this is the operating point, which gives speed omega m4. So clearly you can see R4 is greater than R3, greater than R2, greater than R1. So when you increase the resistance from R1 to R2 to R3 to R4, what happens to speed? You can say at R equal to R1, speed of the motor is omega m1. When you increase resistance from R1 to R2, speed drops from omega m1 to omega m2. Then similarly, when you increase resistance from R2 to R3 and R3 to R4, the speed drops from omega m2 to omega m3 and then omega m3 to omega m4. So therefore, omega m4 is less than omega m3, less than omega m2, less than omega m1. That means as armature resistance is increased, the motor speed decreases. So this is how you can control the speed of motor, simply by putting a rheostat or a resistance, a variable resistance in series with the armature and changing this armature resistance. Increase the resistance, you will get low speed. Decreasing the resistance, the speed will increase. So this is how speed control can be achieved very easily by this method. However, this method is not a preferred method because it suffers from some serious drawbacks. What are the drawbacks of this method of speed control? Let us identify some of the very serious drawbacks of this method of speed control. The first drawback is that as you increase the armature resistance, the speed decreases. When you increase the resistance from R1 to R4, the speed decreases from omega m1 to omega m4. Fine, no problem. But what happens to the slope of the torque speed characteristic? The slope of torque speed characteristics increases. So that if this is the full load, say for example, let us suppose this is the full load torque. Okay. So when you go from no load to full load, there is a large drop in the speed. See, at no load, speed is omega m naught. At full load, corresponding to R equal to R2, this is the speed. And the drop in speed is very large. Similarly, for R equal to R3, there is still more drop in the speed. No load speed is omega m naught. Full load speed is this. Similarly, at R equal to R4, there is a large drop in the speed. So therefore, when you increase the load torque, say for example, this is a particular load torque. When you increase this load torque like this, so speed regulation becomes poorer and poorer. Okay, you can see corresponding to this load torque, this is omega m1, but corresponding to this load torque, omega m1 decreases. Corresponding to this load torque characteristic, omega m still decreases, and corresponding to this load torque characteristic, omega m decreases. You can see there is decrease, more and more decrease in the speed from no load to full load. So that means the speed regulation of the drive or the speed regulation of motor suffers. That means the drop in speed from no load to full load is very, very large, which is called speed regulation. What is speed regulation? It is the change in speed or drop in speed when you go from no load to full load as a percentage of full load speed. It is no load speed minus full load speed divided by full load speed. So the motor has poor speed regulation. In some applications, this may not be acceptable. No doubt you may control the speed by varying the armature resistance. By increasing the armature resistance, you may drop the speed. But as the load on the motor increases, the speed automatically, without changing the armature resistance, the speed will keep on decreasing. As you can see, speed keeps on decreasing when you increase the load on the motor. And that means as you go from no load to full load, there is a significant decrease or drop in the speed. So the motor has poor speed regulation. In other words, the torque speed characteristics lose their hardness. Torque speed characteristics lose their hardness. What does this mean? This means that as you increase the armature resistance, the slope of torque speed characteristics goes on increasing and increasing. They are not parallel to each other. You can see none of them is parallel to each other. The slope goes on increasing like this. So these are not parallel characteristics. If the characteristics are parallel, then we say that they have retained their hardness, but they do not retain their hardness. So the torque speed characteristics lose their hardness. That's why they have poor speed regulation. So this is one drawback. Another drawback is that this method of speed control is highly inefficient method of speed control. Highly inefficient method of speed control. Why? Due to large Ia square R copper losses. You are putting resistance in the path of the armature current, and because of this external resistance, there is a large power loss, copper loss, Ia square R loss in this external resistance. Okay, so you are wasting a lot of power in this resistance. So since Ia square R loss in the external resistance is very, very large, this method of speed control, although it is a simpler method, but it is highly inefficient method of speed control. So efficiency of this method is very, very poor. Okay, it is nowadays considered an absolute foolishness to put a resistance in the path of current. With the advent of power electronics technology, now it has become, it's now considered a foolishness to put a resistance in the path of current. The moment you are putting resistance in the path of current, you are wasting a lot of power in the form of I square R loss. So therefore, this method of speed control is highly efficient due to large power loss in the armature resistance, external resistance. So this is one method of speed control, highly inefficient method of speed control. Second method of speed control is armature voltage control method. I will write here armature voltage control method. In armature voltage control method, we are not putting any external resistance in series with armature. We are not putting any resistance in the path of current. We are changing the source voltage itself, the DC input voltage itself across the motor armature terminals. See, this is the back EMF. This is armature resistance, say RA. And this is the applied voltage, V. Now this V is not fixed, it is variable. We change this applied voltage itself. And this is armature current IA. This is the field current here. This is the field resistance RF. And this is field voltage VF. And field current is IF. So IF is kept, field current is kept constant. IF is constant. So that means flux is also constant. Field flux is also constant. But voltage is variable. Applied voltage across the armature voltage is variable. So we impress a variable voltage across the armature terminals, keeping the flux constant by keeping the field current constant. So when applied voltage is varied, we get the speed control, because we know that speed of separately excited DC motor is given by V by K phi minus Ra divided by K phi whole square into T. Ra we don't change, armature resistance is fixed. This is the resistance of armature winding. We are not putting any external resistance in series with armature. So we are not changing armature resistance. We are changing the armature voltage. And when we change the armature voltage, the speed changes. So because speed is directly proportional to applied voltage. And which component of speed is this? This is no load speed. So this is no load speed. So when you are changing no load speed, that actual speed of the motor also gets controlled. Okay. So therefore you will get these types of torque speed characteristics. This is torque axis and this is speed axis. Again, this is omega m naught, no load speed. Okay, let's call this omega m naught 1. Then what we do, this is at say V equal to V1. Let's say applied voltage is V1. Say it is a rated voltage. Then we decrease the voltage. See, you cannot increase voltage above rated voltage, because if you increase the voltage above rated voltage, the motor winding may burn and there may be insulation breakdown also, because the insulation is designed for rated voltage, and also the armature current will go beyond the rated value and the motor winding will get burned. Insulation breakdown will be there and there will be burning of armature winding. So therefore you cannot go above the rated value. If V1 is the rated armature voltage, you cannot go above this. You can decrease it but not increase it. This is the torque speed characteristic for V equal to V2. This is the torque speed characteristic for V equal to V3, and similarly this is the torque speed characteristic for V equal to V4. And let us suppose this is the load torque. Sorry, this is the load torque. This is load torque TL. It is intersect. This is no load speed omega m naught 2. This is no load speed omega m naught 3, and this is the no load speed omega m naught 4. This is the actual speed. The point of intersection between load torque speed characteristic and motor torque speed characteristic gives the operating point. So this is the operating point for V equal to V1, and this is the speed of the motor omega m1. For V equal to V2, this is the operating point and speed is omega m2. For V equal to V3, this is the operating point and speed is omega m3. And for V equal to V4, this is the operating point which gives the speed of motor omega m4. So what we are doing, we are reducing the armature voltage. So V from V1 to V2, V2 to V3, V2 to V3 and V3 to V4. So there is drop in the voltage. And by doing this, we are reducing the speed from omega m1 to omega m2, omega m2 to omega m3, then omega m4. So in this case, speed control is achieved by changing the no load speed. Here for V equal to V1, no load speed is omega m naught 1. Then for V equal to V2, it is omega m naught 2, and so on. And what about these torque speed characteristics? They are parallel to each other. So it is unlike the first case where the torque speed characteristics were not parallel. No load speed was same, but full load speed was changing. The curves were not parallel to each other. Here the no load speeds themselves change and the curves are parallel to each other. And the advantage is that the drop in speed from no load to full load in all the cases is same. For V equal to V1, V equal to V2, V3, V4, the speed regulation remains constant. There is no, you know, deterioration of speed regulation. Speed regulation is very, very good in all the cases. Okay, because the torque speed characteristics do not lose their hardness. They are parallel to each other. The slope remains same in all the four characteristics here. Only the no load speeds change. So this is how speed control is achieved by this method. So in this method, what we are doing, V4 is less than V3, less than V2, less than V1. So obviously omega m4 is less than omega m3, less than omega m2, less than omega m1. So as voltage is changed, the speed changes. But remember, when you change the voltage, you have to ensure that field flux is constant. So in this case, you have to maintain field flux constant. Changing the armature voltage. By controlling the armature voltage, you get controlled speed. You get a wide range of speed control. Now the question is how to change this applied voltage. In olden days, before the advent of power electronics technology, this it was very difficult to change or to vary the DC voltage because we don't have DC transformers. Okay, in AC it's very easy to change the voltage with the use of transformer. We don't have transformers in DC, so it was very difficult. You must have studied about Ward-Leonard method of speed control. That was one of the methods where which was used for varying the armature voltage, but the method was highly bulky. It required large size. It was inefficient method because for controlling one motor of say 100 horsepower you require two more motors of same rating. So the total number of three motors, bulky, large size, large floor area, large noise level, and so on. But with the advent of power electronics technology, now it has become very easy for us to change the DC voltage. You can use DC to DC converters or choppers. With small size chopper you can use for changing fixed DC voltage to variable DC voltage, or you can use AC to DC phase controlled converters for converting AC into controlled DC voltage and hence controlling the armature voltage of DC motor and giving the speed control. Fine. Now the third method, this was about armature, this armature voltage control method. So the advantage of armature voltage control method is advantages: torque speed, number one, torque speed characteristics don't lose their hardness. We get torque speed characteristics at different voltages which are parallel to each other and they give good speed regulation, unlike armature resistance control method which was giving poor speed regulation. So we get good speed regulation. And second is that this is a highly efficient method of speed control. Highly efficient speed control method. Because we are not wasting energy in the external, we are not putting any external resistance in series with the armature. Armature resistance, no external resistance is there and no I square R losses are there. This is the highly efficient method of speed control. So that's why this method of speed control has got high acceptability in industries. In industries, there are many applications where speed control is required, right? Like in steel rolling mills, woodworking machines, cloth winders, similarly in lifts, in electric vehicles, in electric traction, speed control is required. So therefore, we have to study different methods of speed control of a DC motor, because there are still some applications where DC motors are used, although in in majority of applications, DC motors have been replaced or supplanted by AC motors. But there are still some few applications where DC motors are still used. Okay, and for speed control, armature voltage control is the best method. So the first method of speed control, that's armature resistance control method, and the second method of speed control, that's armature voltage control method, we have studied. The first method is unacceptable in terms of efficiency, that gives poor poor speed regulation and poor efficiency, whereas the second method gives very good speed regulation and high efficiency. However, both the methods give us speeds below base speed. There are certain applications where you may require speeds above base speed. For example, in electric traction, sometimes you may require speed above base speed. How to achieve speed above base speed? For that purpose, we have third method of speed control, which is called field control method or flux control method. Field or flux control method. What we do in flux control method? We change the field flux of the DC motor by putting a variable resistance in series with the field circuit. By changing this field resistance, you can change the field current and hence you can change the field flux. And since we already know the speed of motor is given by V by K phi minus Ra divided by K phi whole square into T. So since you are changing this field flux, field current, so field current you are changing, that means flux you are changing, phi. And by changing the flux, as you can see, you get speed, but you get speeds above base speed. Because originally the flux in the machine is equal to rated flux. When you are putting resistance in series, you are actually reducing the field current. So field current becomes less than rated current when you are putting resistance in series. When field current becomes less than rated field current, the field flux becomes less than rated flux. And when field flux becomes less than rated flux, as field flux reduces, what will happen to speed? Speed will increase. So therefore you will get speeds above base speed. You will not get speeds below base speed. For base speed, flux is rated, and by putting the resistance in series with the field circuit and reducing the field current, you are reducing the field current, and hence you are reducing the flux below the rated value. And when flux reduces, the speed increases, and at rated flux, the speed was rated speed or base speed, and at reduced flux, the speed is greater than base speed. So you get speeds above base speed. Speeds above base speed are obtained by this method. But the condition is that armature voltage has to be kept constant. V has to be constant, and field current and hence flux is varied. In armature voltage control method, just few moments back we have studied, there flux is kept constant and armature voltage is changed. But in field flux or flux control method, voltage is kept, armature voltage is kept constant. What which vary is field current or field flux. Now you may pose a question here that just like armature resistance control method, since we are putting a resistance in series with a field circuit, will it not produce I square R losses? Answer is yes. But the I square or IF square RF losses will be very, very small, because we already know that this field winding is having very high resistance. It's a high resistance winding. And field current is already very, very small. It may be a couple of amperes, maybe 1 ampere or 2 ampere, and it will not produce large I square R loss. And in modern, DC motor drives, we don't even need to put this resistance. We can use a DC to DC converter or chopper, step down chopper, by controlling the field voltage. And by controlling the field voltage, the field current and hence flux can be controlled. And hence there will be no power loss. But anyway, even if you put a resistance in series with the field circuit resistance is already very, very high. So current is already very small, maybe a fraction of an ampere or a couple of amperes. So I square R loss in field circuit is very, very small. Now the torque speed characteristics will be like this. This is torque, this is speed. This is the torque speed characteristic, for example, for rated speed. This is speed axis. This is omega m naught 1. And then if you increase the field resistance, field current will reduce, flux will reduce, and when flux reduces, speed increases. Speed increases above base speed. This is RF equal to RF1. Okay. This is for RF equal to RF1, or let us say phi equal to phi 1. Flux, field flux equal to phi 1. This is for phi equal to phi 2. The slope also increases. You can very clearly see when this flux is reduced, the slope also increases. Okay, that's why the next characteristic I will show you more slope. This is for phi equal to phi 3, and next characteristic will have even more slope. This is for phi equal to phi 4. By reducing the flux, okay, by reducing the field current and hence reducing the flux, you will get speeds above base speed, but the slope of curves will also increase, as you can see very clearly. This is omega m naught 2, this is omega m naught 3, and this is omega m naught 4. Let us suppose this is the torque load torque, this is TL. So what are the speeds? For base speed, for rated voltage and rated flux, omega m1 is the rated speed or base speed, and then this will be omega m2, which is greater than omega m1, omega m3 even greater, and similarly this is omega m4. So therefore we can say that phi 4 is less than phi 3, less than phi 2, less than phi 1. We are reducing the flux from phi 1 to phi 4. Phi 4 is less than phi 3, less than phi 2, less than phi 1. What about speeds? At phi 4 we get speed omega m4, which is greater than speed at omega m3, that's omega, which is greater than speed at phi 3, which is omega m3, greater than omega m2, greater than omega m1. So therefore, as the field flux is reduced, the speed increases. We get more and more speed. So therefore, we get speeds above base speed. So here, flux is varied, but V is kept constant. Remember, in flux control method, armature voltage has to be kept constant. So this is how we achieve speeds above base speed. So therefore, armature resistance control method and armature voltage control method are the speed control methods of DC motors where we get speeds below the base speed. And flux control method or field control method is the method where we get speeds above base speed. There are certain applications where you may require both. For some periods, you may require speeds below base speed, and for some times, you may require speeds above base speed. Example is an electric train and electric traction. So in that case, you have to use both armature voltage control method as well as field control method. You will use armature voltage control method for getting speeds below base speed, and whenever you require this speeds above base speed, you will switch over from armature voltage control method to field control method. So in that case, you will get this type of characteristic. Let us say this is the speed. So you will get constant torque up to base speed. This is base speed. Let me first of all draw, then I will explain. So this is base speed. That is the rated speed. So this is constant torque. T is constant up to base speed, but power is not constant. Pm is not constant. And if you go from base speed to, let us say this is twice the base speed, twice base speed, the torque will reduce, but power will now remain constant. So Pm is constant. So if you want to get speeds from 0 to base speed, which speed control method do you use? We use armature control, voltage control method. I will write here armature voltage control. And if you want speeds above base speed, which method do we use? We use flux control method or field control method, flux control method. Now we know that power is equal to omega m into T, right? We already know this, and T is equal to P by omega m. For example, if you want speeds from 0 to base speed, just few moments back we have seen the best method of speed control is armature voltage control method. This is the armature voltage control method. And if you want speeds above base speed, the the speed control method available with us is field control method or flux control method. Okay. Again, I repeat, from 0 to base speed, if you want to get speeds below base speed, that is 0 to base speed, we use armature voltage control method. In this armature voltage control method, what we do is that flux is kept constant. In this armature voltage control method, flux is constant. Well, what do we change? We change V. Okay. Otherwise, flux is constant. You have to maintain flux constant, and flux should be at rated value. And what happens is that torque is constant, because we know that torque is directly proportional to voltage. Torque is directly proportional to flux. We know the equation for torque is K phi Ia. Forget about armature current Ia. So phi torque is directly proportional to flux. Since over this period we are keeping flux constant, so what happens to the torque? Torque is constant, but power is not constant. Why? Because power, mechanical power developed by the motor, is speed into torque. No doubt torque is constant, but what about speed? When you go from zero to base speed, speed increases. You see, when you go from zero speed to base speed, speed increases. So torque is constant, but speed increases, and as speed increases, power also increases. So since power is directly proportional to speed, as speed increases from zero to base speed, power also increases. So power is not constant. It increases from zero to base speed, but torque is constant. So that's why this region of operation, zero to base speed, is also called constant torque operation. I will write here, from zero to base speed, this region is constant torque region. Constant torque region. I have shown here also T equal to constant. But as soon as you go above base speed, torque does not remain constant. Why? Because above base speed, how do you get speeds above base speed? You get speeds above base speed by flux control method. So for speeds greater than base speed, we do the flux weakening. Flux is reduced. And since torque is directly proportional to flux, since you are reducing flux, so what happens to torque? Torque reduces. So for speeds above base speed, torque does not remain constant. It decreases. Why? Because flux decreases. However, power developed by the motor remains constant. Why? Because P is equal to omega m into T. What happens to speed from base speed to above base speed? Speed increases. Speed increases, but what happens to torque? Torque decreases. And the product of the two remains constant because one parameter increases, another decreases above base speed. So for speeds above base speed, speed increases, torque decreases, P equal to omega m into T remains constant. So that's why I am showing constant, power remaining constant for speeds above base speed. So therefore this region of characteristic or speed control is constant power region. Constant power, constant power region. So therefore, in certain applications, you require speeds above base speed and you also require speeds below base speed. So if your drive has to be driven at speeds below base speed, then you have to go for armature voltage control method. And armature voltage control method gives constant torque region. It operates in constant torque region. And if you want, say now speeds above base speed, you have to go for flux control or field control method. And in the field control method, we get speeds above base speed, but it keeps the power constant. That's why this region is called constant power region. Okay. And for armature voltage control method, when you achieve the speeds from zero to base speed, flux has to be kept constant. And for speeds above base speed, use flux control method. Here voltage has to be kept constant. V has to be kept constant. For armature voltage control method, flux should be constant, and for flux control method, V should be constant. So you get two regions, constant torque operation region and constant power operation region. So this is how we can use armature voltage control method for getting speeds below base speed, which gives constant torque region of operation, and how we can use field control method or flux control method for getting speeds above base speed, which gives constant power region. Okay, so I will stop here for today's lecture. In next lecture, we will discuss about the torque speed characteristics of DC series motors, and we will also study about the speed control methods of DC series motors. Thank you very much.